Hello, welcome to the 7th session of the Introductory Biostatistics Distance Learning course. The topic for today will be hypothesis testing, and we're a little bit ahead of schedule because I've admittedly been going a little bit over the 45-minute sessions that these are supposed to be, so I apologize for that. I'm going to try to stick to the 45 minutes. And since we're a little bit ahead of schedule, we can slow down the pace a little bit. So this lecture on hypothesis testing will probably be extended over to 2 lectures instead of 1. So I'll try to keep to the 45-minute format. Sorry about that. Okay, so what did we do in previous classes? Well, we learned about the basics of probability, the central limit theorem. Remember, the central limit theorem told us that even if our parent population was skewed or somehow not normal or not symmetric, if we took repeated samples and then look at the distribution of the sample means, so repeated samples, so we take a sample, we get a mean. We take another sample, we get another mean, and so on. If we were to do that many times over, the distribution of the repeated sample means would be normal. And that allowed us to get a standard error for the mean, that's sigma over root n, or s over root n, where we use the sample standard deviation, and then from there we were able to construct confidence intervals. Okay, so today, and also in the next session, since we'll extend this over to, we'll talk about rare events. We'll talk about p-values, which you'll see in just about any paper in the medical literature that's a quantitative study. We'll talk about hypothesis testing, obviously, that's the main topic. And then we'll talk about 1 and 2 sample t-tests. 2 sample t-tests. And we'll talk about what that exactly means to do a t-test. Okay, so those are the topics that we'll try to cover today. Okay, all right. So you'll remember from a previous lecture, if I just pull up the picture, we had a situation like this, where if we had the standard normal, remember the standard normal is one that's mean is 0 and standard deviation is 1. That's a standard normal, mean 0, standard deviation 1. Then we have tables that tell us how much area falls in different parts of this curve. And so here, this is cutting off at negative 1.96, and we learned that at negative 1.96 the shaded area represents 2.5%, where everything under the curve, the entire curve is 1, right? Because we learned that probabilities must sum to 1. So 2.5% of the region falls on the shaded black side on the left. Similarly, if I were to draw a line at positive 1.96 over here, this is 1.96, we know because it's symmetric that this shaded area that I'm coloring in would also correspond to 2.5%. Okay, so that's going to be important today as we learn about p-values, so keep that idea in mind. Okay, and so in the last couple sessions, we talked about how we were going to estimate the population mean with the sample mean, and then place a confidence interval around that sample mean. Okay, so now today in hypothesis testing, we're going to consider testing whether or not our sample mean is equal to a hypothesized value. And then we'll see the correspondence between the confidence intervals that we learned before and the hypothesis testing that we'll learn today. Okay. So one example comes from the literature on multiple sclerosis. Okay, so in the normal population, there's this outcome that they measure, and in the normal healthy individuals, their mean score on this kind of arbitrary scale is 55. And so now we want to see if patients who have multiple sclerosis or MS, is their measure on this scale, their mean, is that equal to 55 as well? So we know the undiseased, their mean is 55, but now we want to figure out whether the diseased folks with multiple sclerosis, whether their measure is equal to 55. Okay, so how would we test this hypothesis? Again, the hypothesis is whether the folks with MS have the same mean score as the folks without. Well, we take a sample, right, which is what we've talked about so far. Whenever we do a study, we start off by taking a sample. Obviously, we don't have the time or resources to measure this on everybody, so we find a smaller subset called a sample. Okay? From there, we get summary statistics and then compare them to what we call a null hypothesis. Okay? So we'll see that more as we go forward. Okay? So what are the reasons that there could be a difference? So what are the reasons for differences? If we were to observe differences between the healthy people and the people with MS, what are the possible reasons for differences between groups? Okay, there could be a real effect, right? There's an actual difference. So when there's an actual difference between, the treatment group and the placebo, or the diseased and the undiseased, we want to be able to detect this with our research study. Another possibility, which we don't want, is it could just be due to chance. We picked, suppose we're comparing diseased and not diseased, we picked the diseased with really low scores just by chance, and the undiseased with really high scores, so that led us to believe there was a difference when there actually was not one. Okay. Another way there could be a difference is because of bias. Okay, so that means we didn't obtain a representative sample, so there was a systematic bias. Before, this was chance, right? But this is a systematic difference. Okay, so that's the distinction between these two. Okay, and then we could also have confounding. We'll talk more about confounding as this course goes on. So I won't say too much about it here because we'll talk about it in the future, but this is another reason why we could observe a difference between groups. Okay? So statistical tests are designed to determine if the observed difference between groups, that is to say, the observed difference between our samples, is due to chance or whether it's an actual difference. Okay? All right, so now let's talk about a chance experiment. So we have an experiment. Okay, I'm going to flip a coin. If it comes up heads, I win $1. If it comes up tails, you win $1. Okay, heads, oops, I win $1. Tails, you win $1. Okay, so what if the following happened? We got 2 heads in a row. You probably think, oh, I'm pretty down on my luck because I lost 2 times in a row. What if we got 5 heads in a row? What if we got 15 heads in a row? I won 15 times in a row. When would you start to get suspicious that maybe I'd cooked the game? Maybe it wasn't a fair game. It wasn't a fair coin. If I won 15 times in a row in a coin toss, you might start to get suspicious. Okay? So that's setting us up to talk about null hypotheses. Or null hypothesis. Okay? So in all experiments, we go in with an initial belief. So in that previous example, we believed that it was a 50-50 chance of getting heads or tails. Okay? So we set up a null hypothesis so that it's rejected. So for our study about multiple sclerosis, the null hypothesis is that the mean score for patients with MS is equal to the mean score in patients without MS. Okay? In the coin flip example, the null hypothesis would be that the chance of, or the probability of heads is equal to the probability of tails. And we usually write that as H0, the null hypothesis, okay? So we'll write something, for example, the mean among patients with MS is equal to 55, which is the value for patients without MS. Then we have an alternative hypothesis, which we either write HA for alternative, and then, or some people write H1 as well. These are both alternative hypotheses. And it has two characteristics. One, it must cover all values not included in the null, and it must contain the value we think it's going to happen, okay? So here, if I said the mean, or the null hypothesis, sorry, is that the null hypothesis is that the mean score among patients with multiple sclerosis is equal to 55, then the alternative has to cover all values not included in the null, all other possibilities. Well, all other possibilities means the mean in the MS group is not equal to 55. And also note that I'm using this word mean, okay? This is very important because we'll obviously have some MS patients who have higher than healthy people. We'll have some MS patients who are lower than some healthy person. But our tests are about the mean, okay? So on average, what are people with MS like compared to those without MS, okay? All right. And so in the coin flip example, just to do another example, our null hypothesis would have been that the probability of heads is equal to 1/2 or 0.5. And then our alternative obviously would be that the probability of heads is not equal to 0.5. Okay. So what do we do when we're doing hypothesis testing? Okay. What we do is we assume that the null is true. We start off assuming that the null is true. So here I'd assume that the mean among people with MS is equal to 55. Here I'd assume that the probability of heads is equal to 1/2. So we start off assuming that the null hypothesis is true, okay? And then we collect data and we say, hey, assuming that the null is true, what is the probability of this type of data that I collected, okay? So what does that mean? Let's get a better sense for this, okay? And so then we get a p-value, which is what helps us decide. So again, just to clarify, we write our null and alternative hypotheses, we assume that the null is true, and then we calculate this thing called a p-value, okay? So what is a p-value? Definition is the probability of the observed result or something more extreme under the null hypothesis. So when I say under the null hypothesis, I mean assuming that the null is true. Okay? So what do? I assume that the null is true, I collect data, then I calculate this p-value, assuming that the null is true, and if it's really small, then I say, well, it's likely that this difference between the groups is not simply due to chance and we have an actual effect. Okay? So if the p-value is small, and people usually use this cutoff of 0.05, then we call the effect statistically significant. Okay? So don't worry if this is sounding a little too abstract. It'll make a lot more sense as we work through examples. Okay? But you want to get this this basic idea clear. So we set up a null hypothesis. That's usually a hypothesis of no difference between either the groups or things like that. Then we assume that's true, we collect some data, and then we see what is the probability of the observed kind of data that we had, or something more extreme under the null hypothesis. If that probability is small, what we're saying is, hey, if the null is true, the chance that we would get this kind of data is really small. So then we would reject the null hypothesis, and we'd say, hey, we think there's an actual difference between these groups. Okay? And like I mentioned, people have chosen this 0.05 cutoff. There's nothing magical about this. It's just kind of a convention. But people usually say if their p-value is less than 0.05, then they reject the null hypothesis and say there is a statistically significant effect. Okay? All right. Again, don't worry if you're not really following. It'll make much more sense through an example. Okay? All right. Okay. And again, as we've mentioned kind of in passing a couple times, it's really important that when you design your experiment that you obtain a random and representative sample, because otherwise you might have bias, which is one of the things we mentioned could lead to a difference, observing a difference. Okay? Okay, so what are our steps? These are going to be really helpful as you work through examples. Steps for hypothesis testing. Okay, what are our steps here? Okay, first, we want to state the null hypothesis. State null hypothesis. Okay? And the alternative. Okay? Between the null and alternative, you should have covered all possibilities. So if we say the mean score among patients with MS is equal to 55 in our null, then the alternative has to be that it's not equal to 55. Okay? Because between the two of them, they have to cover all possibilities. Then we want to state the type of data that we're working with. So do we have continuous data? Do we have binary data? And so on. Then, based on that, we can determine the correct statistical test. Statistical test. Then, once we've determined the test, we have our data, we can calculate summary statistics. We want to state summary statistics. Okay, then we'll calculate a p-value based on these summary statistics. This is usually going to be done with our software. We're not going to do this by hand. So here we're using Stata. Then, based on the p-value, you can see how each step builds on the previous step. So we stated our summary statistic, and then that gave us a p-value. Then, based on the p-value, we either reject or fail to reject the null. The null hypothesis. And then finally, we write our conclusion. And again, don't worry if this all sounds kind of crazy at the moment. It's going to make a lot more sense as we work through an example. Okay? All right, so let's do just that. Let's work through an example. Here's our example. And we're going to work through those 7 steps. So the null hypothesis was that the mean score, again, this is some arbitrary score. Whoops, let me erase that. The mean score among those with MS, so this is how I'm writing it. The mean among those people with MS is equal to 55. Remember, 55 is the mean score among healthy folks. Okay? And so we're working, this score that we have is a continuous variable. Okay? So we had to state the type of data we were working with. This is continuous data. Okay? And then we want to ask ourselves, how different is the observed data from the hypothesized value? Okay, and we want to know what test can we use to compare the mean of a continuous outcome to a known value. Okay, so here's the mean of a continuous outcome, and we're comparing it to a known value of 55. Okay, so what kind of test would we do? It turns out that we would do something called a one-sample t-test. Why is it called one sample? Well, you can imagine, let's not get too far ahead of ourselves, but you can imagine we could do a test of the mean score among those with MS is equal to the mean score in those without MS. That would be a two-sample test. But here we're just comparing the mean score to a known number. So that's why we call it a one-sample t-test. But you can anticipate what's coming. We'll then move on to two-sample t-tests. But for now, again, we'll just focus on one-sample t-test rather. Okay? And it's a test for the difference between a mean and a known value. Okay, one-sample t-test is a test for difference between a mean that we calculated from a sample that we collected, test of a difference between a mean and a known value, in this case, the number 55. Okay? Assumptions. So this is something we're going to get used to. Each statistical test has assumptions, and if those assumptions are not met, then we shouldn't be conducting the test. Okay? So what are the assumptions of a one-sample t-test? Well, it assumes that the underlying population distribution is normal. So that is to say, if I could sample every person with MS and make a plot of their scores, it would look like that. Okay? Usually that assumption holds. Another assumption, so let's just call this 1. Another assumption is that the observations are independent. Okay, so that is to say the score of one patient with MS does not have any influence or impact on the score of another patient with MS. Okay, so a situation where that sort of assumption might be violated is if you're sampling people within the same family. We know that people in the same family have a lot of similarities in their health, in their genetic makeup, and so on. So that's a case where independence might not hold, independent observations. So here we want to make sure that we have independent observations. Somebody's score does not affect somebody else's score. Okay? And so this test, the one sample t-test, assesses whether the observed mean is different from what we would expect under the null. Okay? All right. So last week we talked about the t statistic. Remember, we used that when we didn't know the population standard deviation. Okay? And so we can calculate a t statistic by taking the sample mean minus the hypothesized value divided by the estimated standard error. Okay? So what is the basic form of that? Well, here's our test statistic. Remember, we're just working through those 7 steps of hypothesis testing. Okay? So we form a t statistic, okay, which takes this form. T equals x bar. Remember, x bar is the mean in our sample. So we collect a bunch of patients who have MS. We measure this score on all of them. And then we get x bar, the mean score. Subtract off mu, the hypothesized value, and then divide by sigma over root n. Remember, that was the standard error. Okay? And so this here is kind of asking the question, is the observed mean, that's x bar, is the observed mean different from the hypothesized mean, mu, 55 in this case, relative to the variability in the data? That this is encompassing the variability in the data. Okay? So let me just kind of, so this was the observed mean from our sample. This is the hypothesized mean. We know that the 55 holds for the healthy people. We want to know whether it holds for the people with MS. Relative to the variability in the data, this captures the variability. Okay. So not surprisingly, this t statistic has a t distribution. Okay, this test statistic, sorry, has a t distribution. Okay, so therefore we can calculate the probability of the observed result or something more extreme. Remember, that's called a p-value, by calculating the tail probability. Okay. All right, so let's work with real data. So suppose we were to calculate this, and our sample mean for the patients with MS was 54.5. Our hypothesized value was 55. And suppose we had a standard deviation of 12.1 divided by the square root of n, that's the number of patients that we have. We'll call that 200. We had 252 in this sample. And then I can calculate this number out, and it turns out to be negative 0.66. So what does that look like in a picture? Okay, this corresponds to negative 0.66. And so to calculate the p-value, we calculate the probability of the observed t statistic or something more extreme, right? So since we're on here's the middle of this distribution. Since we're on the left side, Something more extreme would be something further to the left, right? That's why we have this blue shaded region. So in order to get our p-value in this example, we say, what is the area in this blue shaded region? What is the probability of the observed t-statistic or something more extreme? So it's this area shaded in blue. Okay? And we can do that. We can calculate that area. Remember, using our probability notation, we would write the probability that t is less than, right? As we go this way, it's less than. T is less than or equal to negative 0.66. And we can get a statistical software package to tell us that that probability is 0.25. Okay? So that's our p-value in this example, 0.25. This is really cool, right? Because we said that a p-value is the probability of the observed result or something more extreme under the null. Remember, the null here is that the mean score among patients with MS is 55. So we calculated that and we got our p-value. And our p-value is 0.25. So what does that tell us? That says that the probability of observing this or something more extreme under the null being that the people with MS have mean score equal to 55, is 0.25. This would happen 25% of the time. Okay? So this is called a one-sided p-value, right? Why is it called one-sided? Because we only looked at this side of the curve. We didn't look over here at all. It's called a one-sided p-value, okay? But in medical research, the vast majority of the time we're interested in two-sided p-values, okay? So what do two-sided p-values look like? That's like so, okay? So that means our p-value for a two-sided p-value, this is a two-sided p-value, this means that our p-value is the probability of the observed result or something more extreme in both directions. So that means here would be negative 0.66, while here would be positive 0.66. Okay? So a two-sided p-value is equal to 2 times the one-sided p-value. Okay? And remember we said the area in this tail is 0.25. So the area in this tail is 0.25. And since I know that, I also know this area in the middle, because these have to sum to 1. Remember, probabilities sum to 1. So this area in the middle, because I have 25% here and 25% here, this must be the other half. Okay? All right. So that's a two-sided p-value. Okay? So let's go back to our steps for hypothesis testing. Remember, our first step was to state the null and alternative. So the null was that the mean score among patients with MS is equal to 55. The alternative was that the mean, sorry, I'm running out of space, is not equal to 55. And again, between these two possibilities, between the null and the alternative, I've covered all possibilities. It's either equal to 55 here, or it's not equal to 55 here, okay? I want to say what kind of data I have. It turns out we were measuring a continuous variable. Remember, we talked about all the different types of variables there were. Continuous variables, there's binary, categorical, ordinal, and so on. Time to event. Okay, so whoops, we have continuous data. The appropriate statistical test here is a one sample because we're just comparing the people with MS to a specific number, 55. One sample t-test. Then we calculate the mean in our sample, and we can write that. Remember, when we calculate something in a sample, we sometimes put a hat on it like that. It's kind of a funny notation. You put a hat on it. Mean score among those with MS in our sample turned out to be 54.5. Then we calculate a p-value. Remember from the previous slide, it was 0.25 plus 0.25. It turns out there was a bit of rounding, and the p-value when we use Stata will be 0.51. Okay? And so this is our p-value. Remember, we always compare our p-value, not always, but usually we compare it to the number 0.05. Obviously 0.51 is greater than 0.05. Okay? So that means we fail to reject. We only reject the null hypothesis when our p-value is less than 0.05. Why do we do that? Because if the p-value is small, we're saying the chance of observing the kind of data we did, assuming, remember, we're always assuming that the null is true, so the chance of observing the kind of data we did, assuming that the null is true, is small. Therefore, we don't think the null is true. But here, the chance of observing the kind of data we did or something more extreme was 0.51. So that's a pretty high chance. So we think, yeah, the null is true. Our assumption was correct. So, but you have to be careful here. We never say that the null is true. Instead, we say that we fail to reject the null. Okay? And why do we have to be careful about our language here? The reason is because we might be failing to reject just because we didn't collect enough information. That sometimes people refer to that as a lack of power. We just might not have enough power to detect a difference. Okay, maybe we didn't collect enough samples. Okay, so we never say we accept the null. Instead, we say we fail to reject it. Okay, so we either reject the null or fail to reject it. So what's our conclusion? In words, the mean, remember, don't forget this word, the mean score among those with MS is not significantly different, sorry, I'm running out of space, significantly different from 55. Which was our hypothesized value. Okay? So now you can see we've gone through all 7 steps. We stated the null and alternative hypotheses. We said that, hey, we're working with continuous data. We only have one sample because we're comparing those with MS to a specific number. So we use a one sample t-test. Then we calculate our summary statistic, which is the mean among those with MS. We got 54.5. Based on that mean, we can get a p-value. That Stata is going to give us that. Turned out to be 0.51 here. Since 0.51 was larger than 0.05, we failed to reject. And then we say, in words, the mean score among those with MS is not significantly different from 55. Okay? All right, so we've completed our first hypothesis test. So what does the Stata output for this look like? Let me pull that up. Here it is. Okay, so here's the state of command that we would type into our command window, t-test, and then this is the variable name in this example with multiple sclerosis. So t-test, variable name, equals equals, we need two equal signs to tell it we're testing whether it's equal to 55 or not. Okay, so here it tells us the mean from our sample, 54.5. The estimated standard deviation in our sample. Here is the 95% confidence interval. Over here it looks like it goes from 52.99 or 53 to about 56. And then you'll notice here, this is a one-sided p-value. While here is a two-sided p-value. How did I know that? I knew that because of the alternative hypotheses. Remember HA, remember HA, which is what's written here, is the alternative hypothesis. Here, the alternative hypothesis that they've written is that the mean is less than 55. Okay? So if my alternative is that the mean is less than 55, I'm working with a one-sided one-sided test. Okay? Whereas here, this exclamation point here, this says the mean, this exclamation point means not. Okay? So the alternative hypothesis here in this area is that the mean is not equal to 55. Okay? So when we say it's not equal, the alternative is not equal, it could be either greater than or less than. That's why it's two-sided. When we say it's not equal, it could be greater than or less than, therefore it's a two-sided test. Meanwhile, when we say it's less than, that's a one-sided test. And here's the other one-sided test for the mean being greater than 55. And we said that almost all the time, unless you have a strong suspicion going in, almost all that, it's going to be either greater than or less than, we're almost always going to work with the two-sided test. Okay? All right. So the comparison of one-sided and two-sided tests, again, a two-sided p-value is just 2 times the one-sided p-value for a t-test. So in other words, here's the p-value, 0.2535. If I take 2 times 0.2535, I get this number here, 0.507. Okay? And a two-sided test is more conservative, we say, because the rejection region is split between the high and low sides. It could be greater than or less than. For a one-sided test, the rejection region is only on one side of the test. Okay? And again, the two-sided test is most common in the literature, in papers that you'll read, even though people sometimes know the direction they're testing. They want to be more conservative. Okay? All right. So what do we do? What if p-value is greater than 0.05, this cutoff, okay? Which happened in this case. The difference between the mean in the patients with MS and the hypothesized value is not statistically significant, okay? So we fail to reject the null, okay? Fail to reject. And again, just to drive this point home, we don't accept the null hypothesis. Instead, we fail to reject it, okay? And the reason is because we just may not have enough data there might actually be a real difference, and we just didn't happen to get enough data to detect the difference, okay? All right. Okay, so now let's do a comparison to the confidence interval. We just did a hypothesis test. How does this compare to a confidence interval? Okay. So previously we had calculated a 95% confidence interval for the mean score among those with MS. So a 95% confidence interval for this value went from 53.0 to 56.0. Okay. And you can see this 95% confidence interval contains, in the middle of this, is the null value, which was 55, right? 55 is in the middle of that 95% confidence interval, okay? So we could have known, we could have come to the conclusion, just based on the confidence interval, that 55 is one of the plausible values because it's contained in the confidence interval. It's one of the plausible values, and we would have known that, hey, we were going to fail to reject our null hypothesis, okay? So therefore, the conclusion that we reach from the confidence interval and the hypothesis test match. The conclusions are the same, okay? So that's a really neat thing, and that really aids our understanding. So we reach the same conclusion based on either the confidence interval or the hypothesis test, okay? So it looks like we're getting close to this 45 minutes. I'll just do a few more concepts, and then we'll wrap this up and continue in the next session, okay? Now let's talk about something in hypothesis testing called type 1 error. Okay? So a type 1 error is when we reject the null even though the null is true. So it's an error, it's an incorrect decision. Okay? So type 1 error is the probability of rejecting the null even though the null is true. Okay? So what does that look like in a picture? Okay? So the area in this tail, remember this is 0.025, and the area in this tail is 0.025. Okay? So the red region in the graph, these are parts of our curve, right? There are parts of the curve under the null. But if we'd observed data here, this would have fallen in our rejection region, and we would have said, hey, this is different. So here we would have committed a type 1 error. We would have rejected the null when the null is true. Okay, that's a type 1 error. Okay, so we want to be aware of the different kind of decisions we can make. Okay, so how can we summarize this? We can summarize it in a 2x2 table. Let's take a look. Okay, so first of all, there's the truth. If we knew the truth, we don't, obviously. Well, that's what we're trying to get in. And then there's our decision. Okay? So the truth is either the null is true, or the null is false. Okay, the null is either true or false in reality. And then our decision, we can either, whoops, I'm kind of running out of space. Our decision, we can reject the null, or we can fail to reject the null. Okay, so we have this 2 by 2 kind of table. Okay, so let's look at what's going on here. Okay, so suppose here's our decision to reject the null, and the null is false. Well, that's a correct decision, right? If the null is false and we reject it, then that's a correct decision. Similarly, if the null is true and we fail to reject it, well, that's a correct decision as well. These are the two spots we want to be. We want to, if the null is false, we want to reject it. If the null is true, we want to fail to reject it. Okay? Now, if the null is true and we reject it here, that's a type 1 error. Okay? This is when the null is true, but we decide, or our decision is to reject. Okay, so that's a type 1 error. And then down here, when the null is false and we fail to reject, that's a type 2 error. And you can kind of get a sense why this one is called a type 1 error. This one is worse. Okay, because in actuality, the null is true. The null is usually there's no difference between the groups. But we say, hey, there is actually a difference. That's a really bad conclusion, right? We say there is a difference between groups when there actually isn't one. That's a pretty bad outcome. So that's why we call that one a type 1 error, okay? And so this is not so bad. This is when there actually is a difference. I mean, it's still a bad outcome. There actually is a difference, but we say, hey, we didn't have enough evidence to reach the conclusion that there was a difference, okay? So it's always helpful to think about this 2 by 2 table. The truth versus our decision, okay? And so we can make correct decisions here and here, or we can make incorrect decisions here and here. All right, that's a lot of, I know this is when you're hearing about these ideas for the first time, they can definitely be very confusing, but hopefully if you take your time with it, it'll start to make sense. Again, we start off assuming the null is true, that there's no difference between groups. Then we collect some data and we see how different are they. We calculate a test statistic. From that we get a p-value, and then if the p-value is less than 0.05, we decide to reject. If it's greater than 0.05, we fail to reject, and then we reach a conclusion based on that. Okay, I will stop here and we will pick this up in the next session. See you then.